Yes, we can.
Yes. So, Rupali ma'am, please.
Yes. It gives me immense pleasure to welcome Professor Somiran Chattopadhyay sir, associated with Jadavpur University, Kolkata. Dr. Somiran Chattopadhyay sir obtained his BTech and MTech degree in 1987 and 1989 respectively from Department of Computer Science and Engineering, IIT Kharagpur. Sir obtained his PhD degree from Department of Computer Science and Engineering, Jadavpur University in 1993. He served as a faculty member in the Department of Computer Science and Engineering, Jadavpur University from 1989 to 1993. In 1993, Sir moved to industry and worked for several reputed organizations, including Motorola Inc. at Arlington Heights, Chicago. Dr. Chattopadhyay sir joined back to the same department in Jadavpur University as an associate professor in 1997. He moved to the Department of Information Technology as professor and head in Jadavpur University in 2001. From 2006 to 2014, Dr. Chattopadhyay sir has also served as the joint coordinator of the Center of Mobile Computing and Communication and as a joint director of the School of Mobile Computing and Communication. Sir has more than 2 decades of experience for serving reputed industry houses. From 1997 to 1998, he was a technical consultant to Mindware, a division of PCL, where he worked as an expert reviewer and for performance improvement of a distributed application project for NEC Japan. He was a consultant in Computer Associate TCG software from 1998 to 2000, where he supported a team of about 10 persons for the development of an intelligent component infrastructure. Professor Chattopadhyay sir led a team of 15 plus developers at Intrasystem India Limited to support a couple of projects in the broad domains of EDA and electron beam lithography from 2004 to 11. He is also a project consultant of prestigious National Digital Library Mission of Government of India. She led the development of an open source C++ infrastructure and tool set for reconfigurable computing released under the GNU GPL 3.0 license. Currently, sir is a visiting fellow of the University of Northumbria, Newcastle, Tyne, UK. He has been a co-faculty in NPTEL DVMS course for the last 2 years. He also served as an academic expert for an online course on DevOps to be deployed by TCS in their TCS ION platform. He was an adjunct faculty at IIT Kharagpur for the distributed system course and a visiting faculty member for the MTech course by IIT Kharagpur, which was offered in distance learning mode. I can go on and on with sir's achievement, but without coming much in a way to you and your learning, allow me to please welcome sir to take on this session. The topic will be delivered by sir is on multimodal machine learning for healthcare, the power of more. I would request now sir to take on this session. Over to you, sir.
Yes, so let me share my presentation and go to the talk right away. But before that, I must thank you for your elaborate introduction, which was not required, and I am grateful for that. So and I thank you for that. So let me share the presentation first, and therefrom I will take over. So. I hope you can see this, right? I hope you can see
sir.
that.
Yes, sir.
Yes, sir.
So the name of my talk today is multimodal machine learning for healthcare, the power of more. I mean, if you have carefully listened to my trajectory of in education, which is not important though, we'll find out that I did not do much in any field. I basically hovered around areas and had had glimpses of that, seen glimpses of that, and enjoyed that to the extent possible, and then I left it. So machine learning is something that I'm working on for the last 5 years, and multimodal machine learning is something on which I never worked, and maybe I'm planning to work in the next couple of years. As a matter of fact, right now I am on Lien from Jadavpur University. I am a professor in a research initiative called TCG Crest, which is a private research initiative, and I work there right now. So machine learning I have seen the broad topics that people have talked about in this particular FDP. I have noticed that a lot of machine learning techniques, AI techniques, will be covered in this FDP. And assuming that, I thought that probably I should say something on which I do not know much, and people will also not know much, and that would be interesting maybe. So I thought I took this topic for my deliberation, which is multimodal machine learning. So I have a schedule for that, and that is the schedule is like this. I have a small introduction, what is multimodal and things like that. Then a core part, which is the technical challenges in multimodal machine learning, a little bit technical in that. Then I'll go to MML in healthcare, and I'll stop with a brief conclusion. One particular, I would say, disclaimer is that my talk is arranged in such a fashion that you may be interested in doing things in it, but many technicalities are not covered in this talk, primarily because this is not a talk where I can provide a lot of technicalities, because then it would have been at least 3 hours talk, and we do that as well. And some of these items that I'm talking about here are naturally discussed elsewhere by stalwarts, and I picked them up. So it is a very nice collection, you can say, if I may say so, and it will be not going to any depth of the matter, but it will go to enough depth at the same time for those who know this. And a little prerequisite, I assumed that maybe you are aware of the standard machine learning techniques like neural networks, maybe a little more CNN, or maybe a little RNN, maybe LSTM, encoder, transformer. If you do not know them, it doesn't really matter. But at the same time, if you are working on machine learning, then these are the things that you need to know. I also want to say one more thing, and that is, nowadays data science is a very vibrant area in which machine learning is applied a lot. If you disclaimers again, that is not the only possibility in doing research. That is not the only direction in doing research. But nonetheless, if you want to do research in machine learning, which primarily will work on data, then you need to have some collaborations or a deep knowledge on 3 things. One would be the domain on which you are applying it. Even if it is a theory work, you have to have a domain to show that your theory works. Then many of us rightly understand that the neural networks and the tools like these are kind of black box. Having said so, it is not so black, it is gray. And if you want to know a little more inside it, you need to know linear algebra to a good extent, as well as optimization and statistical inferences. You have very nice MIT courseware for these 3 things, which you should go. because at the end of it, if you look at them, look at the machine learning open, I mean, make it open and look at it, you will find out that it is basically manipulations on matrices and a lot of stochastic processes that are going in. So if you want to have a little more intention, I mean, I would say insight in it, and not just do trial and error on things, then these three mathematical tools will help you. And actually optimizers are there in your neural networks. And then comes computer science as such algorithms. And then comes your statistics, as I said three things: domain, mathematics, and statistics, and then computer science. So these are the three elements on which you should have a thorough grip or to understand these ML techniques in a better fashion. So let us go to my talk now. And my talk is first is what is multimodal. Now, we experience a lot of things, and the way we experience it, that is modality. Now, in a little more formal manner, it is a certain type of information after all. But not just that, it is that plus the representation format. Most often the representation format in it. If you do not have a representation format, then you have a multimodal, you have a mode, you have a modal information in a particular modality, but you do not really have any computational work possible on that unless and until you represent it. Now, the diagram that you are seeing is quite common, and that is called sensory modality psychology. I mean, as a person, your psychology is guided by all these modalities. We have the 5 sense organs for taste, smell, touch. But even beyond that, you have, sound. Even beyond that, you have appearance, you have memory, you have attention, you have your preferences. All these are different pieces of information that can be used when you communicate. When you communicate, or communicate, by that I mean when you express something verbally or in writing. So life is inherently multimodal. I mean, if you want to say that, ask somebody to go away, then you can show that, a simple text can do that. A text and image can do that. An image can do that. Gesture can do that. So you see, when you say somebody to go away, it can be, just going away is not something that you are saying. You are saying it with a lot of other information which are equally important. So language is just one part of your communication. Beyond that, there are so many other parameters here. Your text is there. I can say as it is shown, a goodbye letter, which may be very nice, and which also may say what I wanted to say. For example, when you read a novel, good novel, then it is picturesque. It reveals the pictorial quality of the content. If we can visualize, then I enjoy it more, right? So mostly people nowadays see video lectures, right? They do not read, because reading is more painful compared to listening to it, seeing a person talking about it. There are losses though in this multimodal phenomenon. For example, one teacher is teaching you, he or she is explaining to you, you are listening to it, vis-a-vis you are reading something and recreating the same thing as if you are teaching yourself. So there is a loss though, and this loss will be there. But maybe for general cases, the loss is less, the gain is more. Maybe for extraordinary cases, the loss is more, the gain is less. And therefore, in those extraordinary cases, people probably would like to do it themselves. Now, So examples of modalities, I think we did not dwell on that. I mean, there are so many. There are language, visual, auditory, touch, smell, physiological signals, other modalities. For example, our talk is based on healthcare. So if I have not drawn that very nice old picture, I mean, you have so many sensors which can be deployed in your body, on your body, which will take data, maybe ECG data, maybe pulse oximeter will give you SpO2 data, will give you pulse rate data. Maybe you have whether you're moving or not, that data can be seen. For example, even your smartphone that you have nowadays is a repository of huge number of sensors which predict about your health as well as what you are doing. In my opinion, the number of sensors that is owned by a person is maximum for the persons who are drivers in racing cars. They have a huge number of sensors on their body, in their body, so that their vitals can be measured from a remote place, similar to probably for the astronauts. Now, therefore, we have so much information, and many times we do our machine intelligence technique applied. We apply them only on one kind of a data. Although we know that maybe that kind of that modality is not sufficient to capture the mood or something. Maybe I would say psychological aspects of the person. For example, if I want to have sentiment just by writing, just by text, how much can you understand your sentiment? If I talk about emotion, I mean, if you say something, if I can see you here talking, then probably I can understand your emotion a lot better than when you write something or when I just get your speech data. Even speech data has intonation and things like that, high level constructs. But just the text has that, but not everybody can write text in such a good manner. So these are things. But then, I mean, we knew this from ages that add modalities and our inferences about what we want to predict will increase. Now, what happened, let's say from 1980, 1990, 2000, 2010, what happened so that this multimodal research, or even machine learning research has gone to such a height? What happened there? Now, what happened is this, that second bullet is the most important to me. Faster computer and GPUs made it possible that you can run those machines in some meaningful ways. Even now, all of you know that without GPUs, you have to hire GPUs from Colab, etc. Because otherwise, when you have a model, you cannot run that particular machine learning application on your own laptop or on your own desktop. That's not possible. So the first idea of neural network came from none other than Alan Turing. He talked about this, but it could not be seen. It could not be experimented on, because we did not have machines of that order which could have deployed millions of, at least lakhs of so-called neurons or units, and find out the computation, make the computation converging in that manner. Once that is possible, next came the first bullet, the large-scale multimodal data sets. After all, if you say that I have created an algorithm which will say that out of 10,000 images, which images belong to dogs, which images belong to cats, which images belong to chimpanzees, object recognition, which images belong to boxes, bowls, etc. Now, if you want to test that your algorithm is correct, first of all, as I said, many of these machine learning tools are almost black box, so you cannot really prove it in a conventional manner like your Dijkstra's shortest path algorithm. You cannot do it in that manner, and therefore you need to only validate through experimentation testing. Now, when I want to test, I need to have a data set, and most of this training, most of these learning techniques, many of them are supervised. By that I mean they need a training data set and they need a testing data set. Now, the moment they need a training data set and a testing data set, the number of elements in that data set must be in the order of thousands of thousands. Only then you can train well, and only then you can test well. Now, again, you can train on a data set, you can test on the data set, you run risk of overfitting. So it may work well in that particular data set, but it may not work. It may not generalize. Change the data set, it will not work. So there comes statistics. You have to show that your algorithm passes a statistical confidence test, so that I can confidently say that this algorithm will work in several data sets with similar kind of parameters, metrics. Maybe it's accuracy, maybe it's whatever. Now, our visual perception is the most coveted perception. We can distinguish lakhs of colors. I mean, our eyes can distinguish lakhs of colors. So our visual perception is a very important perception, and we could not do much with this visual perception till, let's say, 1980, 1990. I mean, we did not. I mean, like I said, object recognition. I said no. Object recognition, for example, finding shapes, for example, these are high-level constructs. These are high-level visual features. Now just let's say an edge, a ridge. These are low-level features, right? Is there a river? That's a high-level question, right? Now, whether you find it through edges and etc., I do not mind, right? So, I mean, these high-level visual features would be recognized, could be classified only, let's say, 20 years back, 20 years, 25 years at the most. And then the linguistic features. The linguistic features were also very, I mean, if you look at the translation capabilities, just Google Translate or something like that. Even now, Google Translation is bad, but Google Translation is a lot better than it was, let's say, 5 years back. So, must be the features, linguistic features, the dimensions must have increased a lot, and therefore we can go to such extents. And therefore, these are the enablers, key enablers, I would say, which led to multimodal research. Now, each one of them, for example, that I could find out high-level visual feature, that I could find out linguistic features which are multidimensional. These are unimodal. So my first talk, my first slide will be just a small recapitulation of unimodal representation. Now, in unimodal representation, just a minute. Just a minute. I lost my window. Yeah, sorry, I just lost my window once. Now, so there are. I just said three of them. One is image, one is acoustics, the other one is language. Now, in language, we have a very important finding in 2013, which is word to vec, which is basically word embedding, which made word embedding possible. Now, embedding your word in a context is so much used by Google Assistant, Alexa, Google Translate, even smartphone keyboard with next word prediction. Now, this word to vec is an algorithm or a method which can efficiently create word embeddings and has been around since 2013. The moment, this actually could relate different words. For example, the synonyms. For example, the stemming, like walk, walking, walked, etc. They are related. So these relations could be done from a given dictionary, and that could be used. As the name suggests, every word becomes a high dimensional vector. And so if any two words are two vectors. Now, similarity is in terms of the standard similarity between vectors, which may be cosine similarity, for example. There are many similarity measures, and that's where you need to take refuge under the course of statistics. So because if you have two waves, how to measure their similarity? If you have two graphs, how to measure their similarity? All these questions are already answered by statisticians, and you just need to find out which metric suits you. Now, image modality, as I said, visual descriptors are there, and the advent of convolutional neural network, which is MLP, which is multi-layer perceptron, with certain special cases. For example, it is not so dense. So it is similar to a neural network or MLP, multi-layer perceptron, but it is a little different, and that actually paved the way of doing a lot of algorithms using images. Also, along with that came encoder, autoencoder, denoising autoencoder, stacked encoder, things like that. And that helped to solve problems where audio signals are involved. Now, I just have a small picture here just to remind you that if it is also something like a neural network. I have input vector, then I have a activation function which may be sigmoid, and I have a weight matrix. So F is just sigma of Wx. So pictorially speaking, it would be a large neural net, and this blue circles would be one layer, and then that encodes. And then if I do a G function on top of that, then it decodes. Now, whether it decodes to the original one or it decodes to a new one, that's a question. That's a question, and maybe it is. I have a sentence as the original x1, x2, xn, then x1 dash x2 dash xn dash maybe a decoding into another language. That's possible, and that is basically the fundamentals of machine translation. Although designing the encoder, designing the decoder, these are very challenging tasks. Also, I must say, in all that I said, ANN, RNN, CNN, LSTM, transformer, encoders, all of them are variants of, in a sense, variants of the neural network, but these are so different that maybe you can find out the neural network there, but they are really very different. So it's possible to see the neural network there, but they are very different. So I just have a small slide here in which I say that if I just talk about unimodal and I have text, the movie is sick, the movie is fair. The movie is sick, really, whether it's what kind of sentiment or emotion am I happy with it? Am I disgusted with it? I do not know. The movie is fair, at least sometimes something like maybe I'm happier myself. My intensity of sentiment is a little higher. Now I'm smiling. I may be sad, I may be happy, I may be doubtful even. And when I say something in loud voice, it may be in disgust, it may be in anger, it may be ecstasy as well. So I really cannot find out from unimodality what is the intensity of the sentiment, or for that matter, what is the emotion in it. If I go bimodal, so I have a smiling face and the movie is sick, then I probably know that it is a happy mood, and I can say sentiment intensity is ++. Now the movie is sick and frowning face can say that I'm I'm disgusted. Maybe I'm angry. I may not say to a very good extent the emotion, but the sentiment is high. Now, if I say the movie is sick and it is a loud voice, then again I do not know much. But if I say the movie is sick, I smile and loud voice, I know that. If I say the movie is fair, I smile and loud voice, I know something. If I say the movie is sick, I have a frowning, face and a loud voice. Then also I know that it's a negative sentiment. By the time it's a good. I didn't like it. So the moment you go for multi-mode, your ability to infer things, infer outcomes becomes much more, which is understandable. But the question is how, what are the challenges there? So that will become our next discourse. I think that is the next discourse, which is we came out of the introductory part, and our next part would be the MMML challenges, right? So let me go there. Challenges. The challenges. We have a very nice article, Multimodal Machine Learning Survey and Taxonomy, by these three people. So they have identified it's an archive. I'm not upset, but it is a very celebrated paper, and I think it has a very huge number of citations. So they say that we have 5 core challenges in our multimodal deep learning areas. So yeah, I changed it from MMML to MMDL because maybe most of the things that I will discuss here will be multimodal deep learning really. Now we will talk about most of them, except I think co-learning. We'll talk about them one by one. But just to say what is representation, we have to summarize multimodal data in some way. Now it is multimodal data. So one mode, maybe which is text, should be complementary to the other mode, which may be image. Now the complementarity is to be preserved, but if the text is redundant or the image is redundant, then that may not be remembered. So we have to represent the data in such a manner that this complementarity and redundancy, they are to be exploited and they are to be used. It is challenging. It is really very challenging. One simple example would be language is symbolic, while image and speech, for example, they are represented by signals or matrices, right? So they are not just one symbol. Now next is next is translation. I'm sorry, this next is translation though. Second challenge, and that's translation. What does it mean? Can you translate or map the data from one modality to another? Can you do that? Now this is subjective. For example, if I have an image, that's one modality, right? I want to find out what could be the text out of it, maybe image captioning. So I want to map the data of one modality of image data to text data. So also find out that given an image data, is there unique text data that is the best fit for that image? No. So even this answer is not unique. So the challenge is just not that task is difficult. Challenge is what is the correct output that is not also known to us. Then comes alignment. Now alignment is something, we'll talk about it, is something that I have relations of I have 2 modalities of data. Now I want to relate them. It may be possible to relate them in a very easy manner, or it may not be possible to relate them in a very easy manner. An idea, I am talking. So my So you are listening to my voice data, and we are looking at a presentation. So later on, I ask you to automatically align my voice data with the image that you are with the simple static image, the PPT image that you are seeing. You have to kind of connect these two. So you have to align my voice with the presentation slide that I'm showing. Very interesting, right? I mean, synchronization problem, syncing problem. Now the fourth one, which is fusion. Now fusion is most common to all of you. We say that multimodal data, they have to be fused. Yes, they have to be fused. So different descriptions, one visual, one audio, one text. They have their own features. Now these features have to be fused, and one composite feature has to be brought. And on that composite feature, I may train my machine learning tool or model so that that machine learning model can answer certain questions based on these data from these two modalities. The fifth challenge is co-learning. It explores how knowledge learning from one modality can help a computation and model trained on a different modality. I mean, I want to work on, let's say, abnormalities in heart rate. So I want to work on ECG signals, and I want to find out which are abnormal, which ECG signals basically reflect abnormal heartbeats. But I don't have this data set right now available with me. It is being developed. What can I do? Can I train and test my algorithm on another data set which is not exactly this? And from that, you can transfer this learning to the actual data set on which I want to work. Or I have worked on an algorithm which works fine with a particular set of images for a particular problem. I want that to work on another set of images for a different kind of a problem. Will that algorithm do? Will that serve my purpose? That is the question. It is also known as transfer learning. Okay, so we'll go a bit deep in these things. Actually, I don't have watch here, so it would be good if somebody from the organizer would tell me that when I go beyond half an hour, things like that, because otherwise I may not be able to complete my talk. So can one or I think the other lady introduced me. Can you just give me? Yeah, can you just send me a signal that half an hour passed and things like that, so that I can.
Yes, sir.
I can.
Yes, sir. Yes, sir.
Do that, please.
Rupali ma'am, Suparna ma'am, we have to note, ma'am.
Yeah. So representation, as I said, it is a summarization and representation and summarization of multimodal data. Our intention is to exploit the complementarity and the redundancy. Now, this representation is very crucial, and it is the backbone of any model. There are challenges. The data that I combine are from heterogeneous sources. One may be ECG data, one may be SPOT data. Their levels of noise are different. Missing data, of course, the quality of data are different. On top of that, the frequency, the frame rate in which these data come to me may be different. So Having said all this, these the different data type coming from different data sources with different levels of noise, different levels of missing data, I have to represent them together. So we have two specific representation mechanisms. One is called joint representation and the other one is called coordinated representation. If I were in front of you, I could have asked you a question, which I cannot do. What can you guess out of these two pictures? But that is not possible in such virtual conferences, and that actually spoils my joy of talking. Nonetheless, so let us look at joint first. Joint multimodal representation. You see that you look at the unimodal data that comes in, like the gesture, like the text annotation. Wow, I like it. Or the audio signal, joyful tone, or the the body language, image, video, audio, text, gesture, everything. They come and they are all accumulated in the same representation space. This space is a joint uniform space, and all of them come here, and so maybe these features are concatenated, they are averaged, backslash taken. After all, a mathematical operation has to be done, right? So we have a very standard but interesting machine known as Deep Multimodal Boltzmann machine, DBM in short, Deep Boltzmann machines. They are most popular for graph model based representations, and that they actually stack what is known as restricted Boltzmann machines as building blocks. These are similar to neural networks. I mean, each successive layers of DBM represents data. I mean, this represents data at a higher level of abstraction. This represents data at an even higher level of abstraction, and so on and so forth. Then why not just a neural network? Why not a DBM? You will find out that DBMs are interesting because they do not need supervised data for training. They do not need training data. And training data, if they do not need, then they do not need annotated data, which is actually scarce. I mean, to build annotated data for any problem, we need to employ a lot of money and a lot of effort, because only human experts can actually annotate them. And time from experts, domain experts, are always a problem in terms of time and in terms of money. So if you say that I have an equally good unsupervised learning model machine, it will be immediately accepted, and that is what is a DBM. So in fact, these DBMs also have another interesting advantage, big advantage, and that is they are generative in nature. Now, what does that mean? If the data is missing, they do not stop. They can generate. Even if a whole modality is missing, the model has a natural way to cope. It can also be used to generate samples of one modality in the presence of the other one, or both the modalities. So it can generate. I do not have those pictures. It can generate one modality if you do not have the other modality, right? But for that, I mean, of course, you have to first get this model done, and then it can do that. Now, let us go to coordinated multimodal representations. Now, coordinated representation process multimodal signals separately, independently, and enforce certain similarity constants. Not only similarity constants, though, some constants on them. So you see that the image and the text are processed, the features are collected by their own machines. Text is by text machines, image is by images machines. Now, then comes a metric. A standard metric is similarity model, which minimizes distances between the modalities in the coordinated space. What do I mean by that? I mean, if I have the word dog and an image of dog, then the representation will try to favor that. The representation will have the distance between the image dog and the word dog will be less compared to the word dog and the image of a cat. So representation will have this complementary information that your word dog and the image dog are complementary in nature. And that is what our original intention was. So as I said, I mean, you can see that, I mean, maybe the cosine distance I calculate, and that is what is it. Now, which one is good, which one is bad, very difficult to say. One needs to study. But I must say this much, that coordinated representation has been used in a lot of places, and that is actually used more than, I believe, joint representations. This example that you are seeing here is basically output of an encoder-decoder pipeline that learns a multimodal joint embedding space, and it has images and texts. So it has a joint embedding space, and a novel language for model for decoding representations from this space. So they represent things as a vector, and since it is a vector, then I should be able to do vector operations. Like I can say this image as a vector, minus blue as a vector, plus red as a vector, and that should give me the images of cars which have red color, like that. So this will not give me one answer, it will give me a number of answers and rank them according to their relevance. That's what it will do. So this is one encoder decoder, and I mean, you can have the CNN here in the place of encoder, things like that, you can do that. So the second one is similar. Instead of the color, it is different, minus day. So basically, it's a vector vector algebra that is in operation. So image is a vector, words are vectors, and therefore it can find out the images with these vector operations. Now come translation. So I have already said that translation is, I have an entity in one modality, and my task is to generate the same entity in a different modality. I will translate. So given an image, you might want to generate a sentence describing it, or given a textual description, like I want to generate an image matching it. It has lots of applications, though. It has applications in speech synthesis. It has applications in visual speech generation. It has applications in video description, cross-modal retrieval, etc. Video captioning is one of the most important and most celebrated use of translation. Now, when you do this, we not only need to understand the visual scene. I mean, object recognition is not the only thing. Object recognition, parts identification, they are important. Maybe a dog in a beach. So I identify from the image that there is a dog, there is a beach. It's a sunny day. I can identify them. But then I have to produce a grammatically correct and comprehensive yet concise sentence. Describing it. So I have to generate a sentence as well. It is not only identifying tag words describing the image. That can be done by CNN. But on top of that, using those tag words, I need to have a meaningful, concise sentence. So for that, I need language enablers. Then only I can do that. So two types of translations are there. One is the left one is called example-based translation, and the right one is called model-based translation, actually, or generative multimodal translation, generative translation. So here I have a translation, a dictionary present. So I have the source, and this will give me the translated words, and then the target will be met. So if I have enough training data, then this example-based algorithms can be used. And such algorithms should be retrieval-based. And after retrieval, I may have to combine them. So retrieval-based or combination-based. Now, retrieval-based algorithms will just retrieve them and show you that as a target. Combine-based models are more complex. They have rules to create a translation based on a number of retrieved instances. So since I need to store all this entire dictionary to search through them, you can guess that the time required by them will be more. The model is heavy and slow. The model will be heavy in terms of footprint, and the model will be slow because there is a lot of searching involved in it. So these models do not provide good results if relevant examples are not there in the dictionary. They will not provide you very good results. On the other hand, the generative approach will have a dictionary, no doubt about that. It will also have a dictionary, but it will build a translational model first. So that model will be used to translate from the source modality to the target modality. So it's a challenging problem. Obviously, it's a more challenging problem than the example-based translation. You have to both understand the source mobility and the target sequence or signal. It may be signal. Such methods are difficult to evaluate as well, because the correct, in general, translation is difficult to evaluate. Why? Because, and for example, if I say image to text, then the correct result is a sentence. Now, the same sentence in 5 words may be written differently by you and me. Both of them or all of them may be correct. Now, how do I say that this sentence is semantically correct? So that leads me to a semantic checker, which is yet to be, which is still not available at a high percentage of accuracy. Our simple paper plagiarism checker, we also call them similarity checker, but they cannot understand paraphrasing and things like that. Beyond a certain length of the document, which is something like a few hundreds of characters, similarity checking machines are not that great. So all these tools that we'll find out in these examples, many of them will not have a great accuracy or a great metric, whatever metric you use, accuracy, recall, F1 score, whatever you use. If it is a classification problem, and if it is a regression problem, you have some data outcome. So that is also not very easy to do. So these are all, unimodal, one language to another language translation is not that great as of now. For example, if I tell you a distance metric between 2 words, that metric itself is not very robust as of now. I mean, if I say I have a word astonish, and I give you a word, let's say, assurance, distance between them, and astonish and astonishing, the distance between them. There are many distance metrics available which are not used nowadays, but a few years back even they were available, in which the distance was upside up. I mean, upside down. Where it should be more, it was less, and where it should be less, it was more. So, after all these classifications are heavily dependent on the distances. So, these are all challenging tasks, even in unimodal and in multimodal, the problem aggravates. So, this is a model-based image captioning. We have a deep, we have a vision deep CNN, as I said, and then the language generating RNN. And then, if you give this machine, we give this image, maybe you assume that you will expect that this will be your output, that a group of people shopping at an outdoor market, and there are many vegetables at the fruit stand. But then that depends a lot on the corpus that you have in your dictionary. If you do not have all, most irritating is if you have, along with this, some corpus, some words coming out of a completely different domain. Maybe let us say, along with these words I have in my dictionary, words like cell, tissue, then some of them might come here as well. And how good is a sentence? How good is a sentence? That is the question. A sentence is how good. Is it correct? Does it make, even if it is correct, does it make sense? So this answer is also not very well given in our NLP domain as of now. Okay, so that brings me to the next idea, next challenge of MMDL, and which is fusion. So in fusion, we will fuse, we'll combine information from two or more modalities to perform a prediction task. Maybe a class, a happy versus sad to classification, or a continuous value, for example, positivity of sentiment through dictation. Now it is really, there are many benefits in it, no doubt about that, because after all, if you have multiple modalities that observe the same phenomenon, then better predictions are natural expectations. That's okay. And that is because complementary information may be available in these two modalities, these two or three modalities, which is not visible in individual modalities on their own. We know that. We have talked about that already. If someone smiles, if another text is there, it is easy for me to find out whether the smile is out of happiness or the smile is out of frustration or something else. Now, another major benefit is, assume that one modality is not so rich in content. Maybe the image is not so bright, not so good, not so bright. The resolution is not so high. Even then, I can recognize the emotion in this example from the other signal. So if the person is not speaking, from the visual signal, we can have an idea. If the person is speaking and the visual signal is not that great, even then, recognizing emotions will be possible to do. So there are actually three types of fusion. One is called early fusion. The other one is called late fusion, which are shown in these diagrams. Also, we have what is known as hybrid fusion. Now, early fusion is something in which the low-level features of the modality are clubbed together. So the real features are not brought out by their independent model, I get some features, some low-level features of the modalities, the data in those modalities. And then I just have a model in which I fuse it. So what I can do, I can just concatenate those features. I can take a max of those features. I can do a mathematical operation and I can do that. And then the model is trained on that. The only benefit of that is that you need to train only one model, train a single model. So the training pipeline is easier. But I mean, at many points of time, although I will have an example where early fusion is used for another reason. If I have high-level constructs, if I have high-level features, then probably I will go for late fusion. In that, the unimodal decisions, these are unimodal decisions. They are already available. Those decisions are fused using a fusing mechanism, right? And I can give the output. It has a number of benefits. It has a number of benefits. First of all, how do I fuse? I can fuse using averaging. I can fuse using voting. I can fuse using weighting based on channel noise. Now, they model individuals. I mean, this will model this modality better. This modality better. So the error in these features are less. So these errors are already minimized. When I go for a fusion, these errors are already minimized. So then I go for a data fusion, which is at a late stage. Now, hybrid fusion attempts to exploit advantages of both these early fusion as well as late fusion. You may ask me, if late fusion was so decidedly good, better, then why early fusion is there? In many cases, we'll find out that low-level features are to be fused, are to be combined. If you fuse high-level constructs, then your problem is not going to be solved. In those cases, one of such cases we'll see. In those cases, we'll go for early fusion. So it is not true that early fusion has no merit in it. Early fusion has some application areas, which may be a little less, but there are. And late fusion has a number of application areas, as I have said. So I have to, that's what I said, I think. So early fusion is applicable on raw data or pre-processed data obtained from the sensors. So it assumes conditional independence between multiple data sources. It assumes that these multiple data sources are not dependent. Now, this assumption is not always true. There are citations for that. For example, video and depth queues are not so independent. So if they're not so independent, then early fusion cannot be done. Now, different modalities can contain information that are correlated to each other at a higher level. The output of each modality can be assumed to be processed independently to one another. So this is an assumption on which early fusion you can do, and it is easy to do. It is easy to do. Simplest form of fusion that we can do, and we have disadvantages. One major disadvantage is large amount of data will be deducted from the modalities to make a common ground before fusion. So in the name of redundancy, we'll actually we may reduce some real important features in early fusion. And if they are really important for your future work, that would be bad. Now, if the data have common matrices, then they can be analyzed by a machine learning algorithm. Now, synchronizing these two modalities is also not that easy, because one may be data signals coming at a faster rate. One may be, let's say, sentences, words coming at a very slow rate. So when you sample, synchronizing them together is also not so easy in case of early fusion. You cannot do that. More so, one data source may be discrete and the other data source may be continuous. Like for example, one may be SPO2 data, which are discrete 98, 99, 100, 70, 74, 73, like that. And the other one is a continuous ECG signal. Then synchronization of these data sources in a timestamp is really very challenging, and we may not be able to do that, and we will go for late fusion of data. It is easy, but I mean, after all, it looks like ensemble classifiers. After all, I mean, I have one classifier for video, one classifier for audio, third classifier for text, and then I find out the features which matches the most. I mean, maybe which is maximal. I can do that. Voting. I may do an averaging if I want. If it is a continuous signal type of, I mean, all of them can be converted to continuous signal. Then I do an averaging. So the technique is simpler in the sense that we do not need to reinvent the wheel for individual unimodal data. We do not need to reinvent that wheel. Now, if the data sources are significantly varied from each other in terms of sampling, in terms of data dimensionality, in terms of units of measurement, then it is good that you find out high-level features from them using their own nice models. And then late fusion will give you a better performance. As I said, errors from multiple models are dealt with independently. Errors are uncorrelated now. Now, different rules exist to determine optimal way of deciding how to finally combine the trained models. So we have to find out some of them. There are rules, Bayes rules, max fusion rules, average fusion rules. These are common late fusion rules. You can invent one as well. And when input data streams are significantly varied in terms of dimensionality, late fusion is simpler and more flexible approach. So with that, we come to, I think, our last one. I mean, well, this is the fourth one. We are not going to talk about co-learning. We'll be talking about alignment only. I already told you that alignment is the task of establishing correspondence between data of two or more modalities of the same event. Like I am talking now, I'm showing you a presentation. The image that I am showing and the voice data that is coming out of my voice. Now you can see one example here. The left-hand side is a text data. Label the bottle. Add 500 ml of water to the labeled bottle. Transfer 1 milliliter of MgSO4 to the 50 ml tube, like that. As if somebody is actually telling you steps of an experiment, and you have a video or frames of that particular experiment that people have shown you. So your task is the one that I have shown here. Add 500 ml of DI water to the labeled bottle that is being shown in this frame. You have to align this text to this frame. That's alignment. So the data from text modality and the data from video or image modality, they have to be aligned. So you have to have a fancy or a magic algorithm by which the elements of the modality 1 will be aligned to the elements of the modality 2. Huge applications are there for this particular thing. Huge applications are there for this particular thing, and therefore this is a major challenge in this as well. The last one is transfer learning. I thought that we'll not describe that in this, and we will go to the next slide. Give me just 2 minutes. I have a dental surgery done, so I have to just wash my mouth once because blood is coming out. So I have to do a little homework, and then we'll come back in 2 minutes, 1 or 2 minutes at the most. Just give me 2 minutes.
Okay, sir.
Dear participants, if you have any question, then please put your question in the chat box or in the question answer session. And Tarak does. Yeah, whenever you log in your device with this online session, then you kindly do mention your registered name. Okay, whenever you are just joining, then please do mention your registered name.
I'm sorry, I just came back.
Yes, sir. Yes, sir. Please.
Yeah.
Rupali, ma'am.
Yeah, I'll resume.
Yes, sir.
So my last part is about health analytics. I'm unsure that I will be able to do justice to it, but let me try. So I start with some success stories where DL has been used in medical imaging in a nice manner. So I'll go from here to here like this, and this one is skin cancer classification. Very nice. I mean, it is state of the art work, so it is used as screening. This is macular degeneration, and then comes diabetic retinopathy classification, then prostate cancer detection, then MRI brain feature extraction, mitosis detection at breast cancer, identification of fetal standard scan planes, evaluating capsule endoscopy videos. Yeah, and then thoraco lumbar fractures detection, last one. So in all these are use of DL in medical imaging for these tasks. So it is heartening to know that actually deep learning would be used by professionals at least to screen, and the state of the technology has reached to this level. However, these are unimodal. These are not multimodal. But I just thought that when I start my health analytics, I'll start with some happy beginning, and then we'll go to the next ones. Now, there is no point of much deliberating what are the different sources of health data. So we have Internet of Things giving me a lot of data. We have wearable healthcare devices. I think very few of you are without the watch that that shows you your heart rate and things like that. That smartwatch is in fashion for quite some time now. Some of my colleagues also wear that. Not frequently, but occasionally. Because, okay. And we have the electronic health records, EHRs in short, imaging electronic health record, medical imaging data. There are, if I talk about medical data, pathological data, imaging data, prescription notes, right? So, and then lastly, a large amount of extractable data obtained from web pages, online forums, and journal articles, right? So they also help. They actually help less compared to their volume, but nonetheless, if you can find out filtered ones, then they help a lot as well. Now, our idea here would be, I will go here. I will take you to take a tour of 4 or 5 different case studies. Now, in these case studies, I will show you how different data of different modality are combined and what prediction was made. They are different. These are chosen in such a manner that the modalities are not the same almost always. The mechanism, the model, the algorithm that I have used is also not the same. They have variance. And I mean, what are the key takeaways? What are the key challenges? What are the core issues that I will talk about in this particular in this discourse? So the first one is cervical dysplasia diagnosis. Now, idea is to improve the accuracy of this diagnosis after all. And we thought that probably, I mean, these are not my works, don't worry about, don't think in that manner, but these are very good works published in very good, journals or conferences. You may know that in computer science, there are many conferences which are referred, which are respected more than the journals, like KDD, like CIK, line CIK, like IJCI, right? So there are in theoretical computer science, stock. So on one side there are ACM transactions, IEEE transactions. On the other side there are Infocom if you are working in networking. So there are excellent conferences in which people kind of publish papers once from India at least, not more than 10 times in their lifetime. So these are from these places. I'll bring out what they have done and why they have done it. That's what I want to do. So it has a deep learning framework, no doubt about that. But actually, what are the data that it has? It has a cervigram data, which is an image data, and observation result from the cervicography. Then it has HPV test and PAP test. What comes out of the HPV test and the PAP test? Evaluation of sample cells from the PAP test, HPV status and HPV single strength from the HPV test, age and pH value. Just this much if I say, you see that the raw medical image data is a high dimensional vector. After all, it's an image data. It's, even in low resolution, it is a high dimensional vector. So, but I cannot ignore it because it contains large amount of undiscovered information. What about the clinical results? Clinical results do not have that much of dimension, but that has instructional information. Do this, do that. I mean, this may be the case. I mean, in very important experts' intuitions are there, right? Doctors, surgeons' intuition is there. I cannot ignore that either. But they are so different, so varied. And therefore, it is a challenge to combine the information from these modalities to perform improved diagnosis. Okay, so let us look at this picture and we'll go to, I mean, many of you can identify this. What is this? Up to this, in fact, this is a CNN, right? What are these layers? Convolution layers. What are these layers? Fully connected layers, right? And on the top, this is image data, and these are non-image data. Age and pH value, the one that I said, HPV signal strength, HPV status, observation result. Now, what is the dimensionality of these of this layer? Huge. As I said, as you can see, 4096. And what could be the dimensionality of this input? 13. So what do you need? You need to change. You have to kind of do something so that they can be fused together, right? So the key takeaway is that I can see. So first of all, they used the ALEXNet for feature learning. It has 5 convolution layers, 2 fully connected layers, and a final 1000-way softmax layer. Now, the cervigram dataset is relatively small compared to the general image. We follow, so you see the dataset is not available. For cervigram dataset is small, but you are using a CNN that needs a lot of input data, training data. So what I do, I train it the model is trained on ImageNet classification task. Is it the cervical data? No, it is not. It is a different data set. I pre-train the model using that and replace its output layer by a new two-way softmax layer. And that model is transferred to cervical data set, assuming that it will give me good result. Co-learning, transfer learning in place. Then, since we have got a 4096 image feature embedding, to reduce it with a non-image data, we have to fuse it with a non-image data. So we have a fully connected layer FC8 with 13 units on top of FC7. That's what I added. So that is the fusion. So that is the fusion that I have done, right? So these are the takeaways. The question is, what kind of fusion is it? You look at it again. What are these? JFC1, JFC2? These are joint, fully connected layers, you know. So what kind of fusion is this? This is early fusion. This is not late fusion. This is early fusion. Now, why early fusion? That is answered here, that what you could do, the 13D CNN feature, 13D non-image feature could be directly concatenated and could be fed to a linear SBN for classification. It is seen that this does not give me good result. In another, so that would be late fusion. In another, I could have a learning strategy in the image modality to use a neural network, and so in the image modality and then the non-image modality, we can have separate models and then combine them with CNN features for the final classification using softmax. So one is a neural network, one is CNN, club them just by softmax. So what would happen is the correlations within the group of modalities is not taken care of. But unfortunately, the data in these different modalities have a high correlation, tighter correlation. The visual features of the image can be treated as a complementary support of your HPV or PAP test. That is why they proposed an early fusion network, and deep neural networks was used. 2 deep neural networks were used to learn the highly nonlinear correlations across all modalities. So these are deep neural networks, and then the diagnosis is given, right? So let me talk to you about one more thing. I think I'll go out of time after that. So one more thing is continuous patient monitoring, a different thing. It's not diagnosis, continuous patient monitoring. Now, in an ICU setup, you'll find out that ECG is running, other real-time vital signs are also monitored, medications are done, given, interventions are done, and I want to model such data. This data is high density data because it's almost big data, because I get it every second, every millisecond I get this data. They are heterogeneous data, and I need an interoperable model. The integration of this high density monitoring data with discrete clinical events. Clinical events are discrete. I give a fluid, I give an injection, I give I do a diagnosis at a given point of time. So those are discrete clinical events. They are challenging but potentially rewarding because they give me interesting information that at that point of time this injection was given. So that's an attention point. That's a guidance point as well. So we propose, the authors propose a recurrent attentive and intensive model. We should know attention in use of attention in neural networks or deep learning models. Now, it is not necessary that attention will be incorporated only in deep neural networks. Attention can also be used in non-deep neural networks as well. Attention is very often used with LSTMs, however, because LSTM is known for remembering the sequence to an extent, right? So, and this is an example where data is coming in sequences at different points of time. Data are coming, and I need to remember those points because, as I said, the critical intervention periods are the ones which are very important. They have to be. I mean, I need to remember that, particularly from one critical intervention to another critical intervention. I need to remember. Not only that, I need to remember what happened in the 5th critical intervention, in 6th critical intervention, and the 7th critical intervention. That I need to know. So that is why they used a recurrent, attentive, and intensive model. Now the diagram is like this. If you look at it, so the ECG is, I mean, they only looked at the ECG first, and others they looked at only for. I mean, this is the only thing that is continuous. They looked at the others they looked at. I mean, not as a continuous thing. Now, these are the irregular clinical events, intervention, or they ask for a lab measurement, they get some measurement and things like that. Now I have a multimodal input processing, and we do not have. I mean, you remember this. I'll come back to this. The key takeaways is this: attention is one of the most useful mechanisms that launch interoperability in deep neural networks. Right? Extensive attention-based deep models have been developed for images, audios, and videos, machine translations as well. Now, you also can do RNN GRU. You can also do that, use that for improving predictive accuracy. Well, let me tell you that interpretation of what happened, that is also very important. I mean, the way deep learning models are treated as black boxes is not good for us. We need to know, we need to interpret, how did you get to this result? So now interpretability of neural networks is a big area of research. Now, without that interpretability, it is difficult to justify why this model and not that model. Now, therefore, a graph-based models are important nowadays. Some of them are RNNs. GRU is one of them. RNN CRG is there. So there are many models which look at graphs in which the interpretation is embedded as links. Now, in this particular model, however, the attention mechanism is using MLP, not an RNN. Now, that is because the input data are continuous and recorded sequentially given each channel. Now, when I integrate the streaming and discrete EHR data, the problem of multi-resolution produced in data integrations could be solved by a combination of refining high-density inputs into low-density representations and filling sparse inputs with smooth missing values. So there are standard techniques for these things. You can do that. One more, so attention is there, that is one. But if you look at this, there is guidance matrix. Look at this guidance matrix. What is this guidance matrix all about? Now, guidance matrix is a two-row matrix. The first row is for the lab test. If the cell in the first row is 1, lab test was newly measured, otherwise it is 0. And if that matrix has 1 in the first row, the second row, 0 is the first row, 1 is the second row, then in that particular time frame, an intervention was initiated with the setup and 0 otherwise. And now look at the premise. An intervention initiation and can include a new medication administration, IV input initiation, ventilator initiation, etc. The intuition behind this matrix construction is to locate potentially important episodes that could influence the final prediction. Now, did I tell you what are the predictions that they wanted to do? They wanted to do predictions like organ failures and length of hospital stay or ICU stay. These are the two predictions they wanted to make. Any organ failure that they wanted to predict, and they wanted to predict the length of the hospital stay. And that is how they predicted it. So they wanted to predict it. So I think I have two more, but there, I mean, on a similar line, I have the, naturally I will share these slides to with the organizers, and you can have a look at that. Unfortunately, I thought of, but I did not. I did not have a reference list for this. I intentionally did it. I mean, if you would ever look at these slides, you can search for using some keywords, and you can get to the document very easily. And the only document that was most important was the archive article. I told you about that, in which all the challenges are very nicely articulated. As far as conclusion is concerned, it's a brief conclusion. So there is a power of many. The sum of the parts is more than the whole is more than the sum of the parts. So if I even have somebody speaking and doing some gestures, so what he is doing, if I want to do that, I have to do a voice recognition, I have to do a non-semantic content emotion, I have to do an auto annotation, I have to do expert behavior learning, I have to look at different modes like gestures and things like that. Then the models have to be found out, have to be given to me by experts. If it is a game, then players. If it is education, then learners. If it is a theater, then listeners. So that has to be. So if you do all this, then you do this. And the other one is, what is the framework then? What is the AI fusion framework then that I have in my mind? It is if you look at it, it is a data-driven insight. So who will give that insight? Machine learning algorithms, unsupervised, semi-supervised. Evaluation is a challenge there. You need domain knowledge experts, domain knowledge acquisition, modeling, reuse, knowledge representation, and reasoning, ontologies. All this will be important as far as domain knowledge is concerned. Now we have cognitive models. We have computational linguistics. We have behavioral psychology. We have organizational psychology. We have consumer psychology. We have pedagogy. We have sociological inputs. And then on everything on top of a very high performance computing that you have to do it. Now I have a number of tasks at hand now from industry. One tells me, for example, that I have a huge data from news, blogs, Twitters, etc. about the market, and I have a continuous data from the market for the last 10 years. Now, can you tell me from the end of today to the beginning of tomorrow's stock market, if you know all that, then what is the beginning? What is the movement, directional movement, up or down in the stock market? So first thing I need there, I said, is a market psychologist, because my plan is to find out the sentiments and emotions that is built in those news, Twitters, etc., and to fuse them together. So again, two modes I'm taking: sentiment and emotion, very related though. And then I want to fuse them together, and I want to predict just the movement, upward movement or the downward movement. If you work in fintech domain, you will find out that predicting stock prices is impossible. So such a frequency of that data, such a velocity of that data. So that is possible, and that is done by exclusive researchers in Tower Research International, things like that. But they do not publish papers. They do not show that way. They will give it to exclusive persons like Mukesh Ambani or Rakesh Jhunjhunwala, people like them. They will not give it to general public. So what it takes to once again, I have psychometric data. Someone has come to me, giving me psychometric data and the voice, and asked me to find out their credibility as an entrepreneur. The entrepreneurial credibility I have to assess. And none of them have come from a very XYZ. They have come from the market leaders. So you may assume that one can have, one came from something like World Bank. So it's doable. They think it's doable, and we have to do that. So challenges are immense, and what I see in my lifetime, I'm looking at AI from 1980s when it had its heyday. Then it went to a gloomy age, and then again it was reincarnated in a new form. Now the form is data to AI, computational model of AI. So what happened to cognitive science to AI? That's still there, but it's a little in the back foot. But without that, many of us believe that real machine learning is an impossibility. So our final goal, therefore, is from AI to intelligence, right? And that is not AI to natural intelligence. So, I may not see that. I hope that sometime some people will actually gauge into that particular phase someday. So thank you very much. I'm very sure that it was a complete waste of time, but that's what my duty is, to make you wasting time. Thank you very much.
Thank you very much, sir, for enlightening us with your valuable knowledge. We are really enriched and really inspired. And with due permission, I will be taking some questions.
Just a minute.
From.
Let me stop sharing. That's,
yes, sir.
Can I stop it? Stop. Let me stop sharing. Yes. Otherwise, you could not see. Yeah. Yes.
Sir, with due permission, I will be taking some questions from our participants.
Since there is no lunch break, people will not go to lunch.
Sir, we will take lunch break after some time.
That's true, but nobody is going to a place for taking lunch, so everybody will take his or her own lunch. Yes.
Sir, we have a raised hand from Pramod Pal. I will allow him to speak.
Yeah.
Hello, sir.
Hello.
Sir, what is the implement through the deep learning, and also we use the swarm intelligence?
Okay, you want to have swarm intelligence as well as deep learning together, right?
Right.
Yeah, they different swarm intelligence for that matter. Those are from the domain of soft computing. Doesn't matter. I believe that you can find out. You do not classify using swarm intelligence. You get the features. You get the features. You get the features there. You get the features and stop at that. For the ultimate outcome, you come back to two things you can do. Either you have the features from those techniques and combine it with the DL, or in the DL, do not classify, do not get the outcome. You can stop. You can stop and get the feature sets.
Okay.
And then you go to the soft computing technique to have a churning of their own mechanisms.
Okay,
but it would be a very nice start. So nice stuff. I have not seen much of such works. Although I'm very sure that somebody will be doing it, but it is not very much in fashion. So if you can show some problems, this gives you a remarkable performance. That will be very well taken.
Yeah. Thanks for very informative knowledge for us from your side. Okay, nice. Thank you, sir. Once again.
Thank you.
Thank you, sir. Participants, if you have any questions, you can write down in the chat box, or you can raise your hand to ask questions directly.
They're frustrated. No, sir, absolutely not.
Absolutely.
So, sir, would you please share your email ID? Then, if any participant
I will give you the slides. Don't put the slides right now as